Okay, now I want to go over a few of these graphs, and before we diving into a lot of equations, let me draw a few graphs for you showing what you might expect to see in a case where you have acceleration, what happens to velocity and position. So let's suppose you have a constant acceleration. And let's suppose, to make it simple, that the acceleration is about, let's suppose it's 2 meters per second squared. Now I can make 3 graphs here. This time I'm going to make an acceleration versus time graph. So I'll plot the acceleration versus time. The acceleration is constant. I said it was constant, so it never changes. Okay. Now this is the kind of thing you might expect to see if you had, say, a ball rolling down a hill, or if I had train, instead of the train rolling down a very long hill, a very short hill as I showed before. Suppose it was rolling down a very long hill. Well, we might get the same acceleration along the entire hill, all the way down it goes. So the acceleration is constant here. What does the velocity versus time graph look like? Well, I know that the velocity, the slope on the velocity versus time graph is equal to the acceleration. The acceleration here is positive, so, and I didn't label this, but this here is going to be 1 meter per second squared. This up here is 2. Okay, now the velocity, what's going to happen to the velocity? Well, I know it's going to increase. Suppose I start with a velocity which is equal to 0. Well, if I do, then that means at the starting time, t equals 0, velocity is equal to 0. If the acceleration is positive, then the slope on this velocity time graph has got to be positive. If the acceleration is constant, then the slope has to be constant. And something with a constant slope is always a straight line. If the slope changes, then there must be a curve. But in this case, because the acceleration is constant, the slope here has to be constant. Now, what happens to the velocity after some period of time? Let's take 1 second. If I wait 1 second, well, let's see. The acceleration is 2 meters per second squared. So the slope, the rise over the run, must be 2 meters per second squared. The run is 1 second. And what's the rise got to be? A equals delta V over delta T. In this case, delta T is 1 second. A, I said, was 2 meters per second squared, so actually this works out if I have 2 meters per second as my delta V. So delta V, the change in velocity from the start to 1 second, is equal to 2 meters per second. That's the rise, that's the increase in the velocity. If I wait 2 more seconds, how fast is it going? Well, if I wait 1 more second. If I wait 1 more second, then the velocity increases by exactly the same amount. So again, the change in velocity going from here up to the final value up here, the change in velocity is going to be 2 meters per second if the change in time is 1 second. So now I'm at 4 meters per second. So after 1 second, it's moving at 2 meters per second. After 2 seconds, it's moving at 4 meters per second. You can calculate this easily if you rearrange this formula here. So the velocity at any time is always equal. If you have constant acceleration, if you have constant acceleration, the velocity is equal to, I can multiply both sides of this equation by t, and I get velocity is equal to a times t. So if I wait 1 second, velocity is 2 meters per second times, 2 meters per second squared times 1 second. Okay, this will become useful in some of the more problems. Let me make finally a position time graph for this same situation. Now this is tricky. The slope on the position time graph is equal to velocity. So at the start, the slope is going to be 0. But as the velocity increases, the slope on this graph is going to have to increase. So that means there's some curvature. It gets steeper as the velocity gets higher. The velocity keeps on rising, so this curve actually keeps on getting steeper and steeper and steeper, and I can't plot this curve on the whiteboard here without running into the rest of my work here. So now we don't know exactly how to calculate x, how the position changes with time if we have constant acceleration yet. For that, we're going to have to use some algebra. So we don't know how to figure out what x is at different times. If we start with a velocity equal to 0 and have a constant acceleration, again, the velocity at any time can be calculated by multiplying acceleration times time. But we're going to figure this out in the next video.